I will continue.
This meeting is being recorded.
Okay, so first of all, I would like to thank Alexander for inviting me to this seminar, and I'm very glad to present a talk. So what I'm going to talk about is a bit more applied topic, because in the last 13, 14 years, my main research field was probabilistic weather forecasting, which was more connected to statistical modeling. However, here I will provide something which is more related to mathematics. And this is the joint work with Martin Leutbecher from the European Center of Medium Range Weather Forecasts. So, to start with, I will explain a bit about these issues of weather forecasting and these fair scores. I will provide some case studies about the use of these scores with real-life data. And I will provide also a different version of scoring rules, which is a box-ordinate transform. And the usefulness of this transform will be demonstrated both with simulation result and with verification result using the operational weather forecast. So, to start with, because probably most people are not involved in this topic, I would like to say a few words about probabilistic weather forecasting. And to start with, you can see here on the left-hand side, ECMWF temperature forecast for Kyiv. And when one thinks about the weather forecast, then has in mind something like these curves here in a top panel figure. So, which is a kind of point. Forecast today is Wednesday afternoon, and these were made this forecast on Sunday late afternoon. However, the problem is with this forecast, they are outputs of a complex system of a numerical weather prediction model, which is a complex system of partial differential equations, which, to be honest, I don't really know exactly what we get, just the data. But anyway, when you see this curve, you don't know how certain can you be in the outcome of the forecast. So what is the forecast uncertainty? And to mitigate this problem, in the last 30 years, Weather Center started to issue so-called ensemble forecasts. And these forecasts are obtained from multiple runs of this numerical weather prediction model with different initial conditions and model parameterization. So you get a set of forecasts. And this is a kind of probabilistic forecast, because you can estimate forecast uncertainty or probabilities of various events. So what you see here in the lower figure is again the same temperature ECMWF ensemble forecast for Kyiv. And you can see that they were initialized on Sunday noon. And by today, we get a bit more uncertainty here. But as time goes by and the forecast horizon becomes longer, you see that for Saturday noon, it has quite a large uncertainty. So you can estimate the probability that the temperature will be above 10 degrees Celsius. And recently, the most advanced weather forecasting system service is the European Center for Medium Range Weather Forecast. It's an intergovernmental European organization financed by 34 countries, and national math centers get forecasts from them and then modify them locally. And recently, its global integrated forecast system configuration is the following. For the whole globe, they produce 51 medium range forecast, which means up to 15 days on a 9-kilometer resolution, and 101 extended range forecast up to 46 days ahead, with a 32-kilometer horizontal resolution for the whole globe. But obviously, one has to evaluate this forecast, and this evaluation is performed with the help of proper verification scores. So the question is, what do we mean by a proper score? Now, assume we have a weather quantity y at a given location, say Kyiv, and time point 5 p.m. today, and we have a corresponding observation. And you get somehow, as a prediction, a predictive CDF or PDF with a given lead time. For instance, yesterday noon was initialized a forecast for today at 5 p.m. And obviously, if we have an ensemble forecast, we can just get the sample CDF. And the scoring rule naturally is a function that assigns a numerical score to the pair of a forecast and a corresponding observation. And we call it proper if the expected score is minimized if the predictive distribution matches the distribution of the observation. And strictly proper if equality holds if and only if they are equal. A famous example which is well used in atmospheric sciences is the continuous rank probability score, defined in the following way, and somehow it compares the predictive CDF with the CDF or the Heaviside function corresponding to the observation. And if we have an ensemble forecast, we have to get the empirical CDF of the ensemble. And the continuous rank probability score is a strictly proper scoring rule for a large set of probability distribution. Our object of our studies will be the so-called logarithmic score, or ignorance score, which is the negative logarithm of the predictive PDF evaluated at the observation. And which means when we minimize the logarithmic score, we maximize the predictive PDF. So we do, by minimizing the logarithmic score, we can get a maximum likelihood estimator. And it's proper, obviously, because when you take the expectation of the logarithmic score and the predictive PDF is the PDF of the observation as well, we can get exactly the differential entropy. And for the differential entropy, this equality obviously holds. So it's a strictly proper scoring rule. Now, and we will go on with this logarithmic score, because when you score ensemble forecast, several questions arise. For instance, what happens if we change the ensemble size? So moving from the 20-member ensemble to a 100-member ensemble. Why it's important? Because ensemble generation, especially for the whole globe, is really costly. At the ECMWF, one forecast of all products takes on a supercomputer around 2.5 hours. And usually when meteorologists do some experiments, they start with a small ensemble, check the properties, and try to generalize it to a larger sample size. The next question is, what is the explanation of this effect? How can be estimated? And another thing, how should the forecast be compared between the systems with different ensemble sizes? ECMWF uses 51 members, whereas the German Met Service uses members, Hungarian Met Service uses 11 members. And if we want to compare the skill of forecast for the same location, so the matching forecast, then we have to take into account these differences in the sample sizes. So that's led to the idea of the ensemble adjusted CFPS. So it provides estimates of the expected scores for a capital N member ensemble based on a smaller ensemble size. And also it led to the notion of fair scores, which means with capital N goes to infinity, and these are optimized if the members of the evaluated ensemble behave like draws from the same distribution as the verifying observation. And concerning the log score, the first result were due to Ziegert et al. From 2019. They derived the ensemble adjusted and fair logarithmic score for Gaussian forecast. So the idea was the following. You have a Gaussian forecast, which you assume that it follows a normal distribution and member ensemble forecast. It has a sample mean, sample variance. Well, it is not unusual that we consider a forecast to be Gaussian because, for instance, temperature is considered as Gaussian, or atmospheric pressure is really considered as Gaussian. So it's not a huge restriction. And of course, this is the theoretical version of the logarithmic score. So it was the negative logarithm of the CDF of the Gaussian distribution. But obviously, when we have an ensemble forecast, what can we do? We estimate the mean and the sample variance, and this is the so-called sample logarithmic score. And what Ziegert et al. Derived is the fair version of the sample logarithmic score. And I hope it's visible on your screen that there are some blue parts here. And these blue parts are the deviations from the original logarithmic score. So we have a modification here. We have an extra term here, where this psi is just the d gamma function. And what was the reason of modification? The idea was the following, that the mean of this sample fair logarithmic score is exactly the theoretical one, which means it is an unbiased estimator for the theoretical logarithmic score. So that was the starting point from our studies, and we want to generalize it for multivariate forecast, for multivariate Gaussian distribution. So you have a p-dimensional observation, and you have an n-member p-dimensional Gaussian forecast, and for simplicity we assume that the covariance matrix is regular. So again, you have the ensemble mean, ensemble covariance matrix. Of course, it's trivial. This is the log score for the theoretical distribution. And this is the sample logarithmic score for them using the unbiased estimates of the mean and the covariance matrix. And this is the condition we should find a modification of this sample logarithmic score, which is an unbiased estimator of the theoretical one. So we started to analyze the mean of this sample logarithmic score, and we had the following decomposition. Okay, this part does not depend on the ensemble, so it's trivial. We have the log of the determinant of the covariance matrix, which represent the sharpness of the forecast, because it's somehow related to the spread of the forecast. Imagine in one-dimensional case, it's just log of the variance, and the smaller the variance, the sharper, the more certain the forecast. And the second term is a reliability, which means kind of a Mahalanobis distance between the observation and the forecast mean. So the closer to zero, the more reliable the forecast. So, and we want to estimate the expectations, which is pure multivariate analysis. So if you take the expectation first of this reliability term, it's easy to decompose in this way. So you have here the sample mean and the theoretical mean, and here the randomness comes from the sample inverse of the sample covariance matrix. Obviously, sample mean is Gaussian. N-1 times the sample covariance is a Wishart distribution. So its inverse is an inverse Wishart distribution. So when you consider this squared Mahalanobis distance and multiply by n, you get a Hotelling t-squared distribution, and which is closely related to a classical F distribution with parameters p and n minus p, which means this part has a modified F distribution. It's easy to calculate the mean, whereas this has an inverse Wishart distribution, and one can find that this is the mean of the inverse Wishart distribution. That is, the mean of the reliability is the following, and again, by blue, I indicated those parts which differ from the theoretical reliability, which is 1/2 times this component. A bit more interesting is the log of the sharpness, but again, we found a nice result that the distribution of the determinant of the empirical covariance matrix has the following form, where these psi i's are chi-square distributions, independent chi-square distributions, or gamma distributions, as you wish, special cases of gamma distributions. So when you take the logarithm from the product, you get the sum, and you get the log of the chi-square distribution, and the mean of the log of a chi-square distribution or a gamma distribution can be expressed with the help of this d gamma function. That is, the mean sharpness is the theoretical part from the log score, theoretical sharpness, plus this term, where this phi p is exactly the multivariate d gamma function. So, to summarize it, this is the theoretical logarithmic score, and what you see here is the sample logarithmic score. And again, the blue parts are those which are the deviations. So when we correct them, we get the fair logarithmic score, and now the mean of this fair score is exactly the theoretical one. So it makes the fair score an unbiased estimator to the theoretical one. And here I have a reference to our paper which appeared last year in the Quarterly Journal of the Royal Meteorological Society, where we give most of the result I'm going to present today here. So that was one part. The other issue, when we want to compare ensembles of different size and assume two forecasts coming, two samples following the same Gaussian law, we have a n-member ensemble and a capital N-member ensemble, so say smaller and the larger ensemble. Obviously, if we take the sum logarithmic scores, their means will differ. Just remember this formula. Here n appears everywhere. So in that way, we were able to consider the so-called ensemble adjusted logarithmic score. So we have a small sample size, estimate the logarithmic score, but this estimator will have the same mean as the mean of the large sample logarithmic score. So it's a kind of a better estimation or good approximation of the log score for the larger ensemble size, which we usually cannot afford. So, and again, all these calculations come from the previous one. And if capital N goes to infinity, we span the large ensemble size to infinity, we exactly get back the fair score here. So in this way, we gave a tool which might extend from a small size ensemble to a large size ensemble and estimate the logarithmic score without generating the larger ensemble sizes. And the next question, how the scores depend on the ensemble size? For instance, in the reliable case. Reliable case means that we have a perfect situation when the forecast and the observation follows the same Gaussian law. We have the theoretical score for this forecast, and obviously it still depends on the observation which follows the same Gaussian law. So we can take the mean theoretical score when the mean is taken with respect to the observation. And we can take the mean of the empirical score with respect to the forecast and taking the mean with respect to the observation. And we can check the deviation. And again, short calculation shows that this is the difference between the mean score for an member ensemble and the mean theoretical score. And from the properties from the Taylor series expansion of the d gamma function, one can derive that this difference has this very approximation. So it depends on the proportion to the square of this dimension and reverse proportion to the ensemble size. And we checked how good is this approximation. So this is the approximation and this is the truth. And you can see the accuracy of the approximation. So this is the approximation and what you see, the true deviation. And you can see, so 1-dimensional, 2-dimensional, 3-dimensional, so, and here you have the ensemble sizes. So 1 dimension kind of 100-member ensemble provides a perfect match with the approximation. Well, even for 2-dimensional, we are fine, but as the dimensions increase, we need larger and larger ensemble sizes. So for 20 dimensions, we need kind of around 500-member ensembles, which are not really feasible. The maximum is the 101 I showed, but on higher resolution, the 51 is the maximum possible. So, and in that way, so this was the theoretical kind of part. And now we wanted to test our result, the behavior of this fair score on real live data. And we considered some case studies. And as case studies, we considered the ECMWF real-time extended range forecast up to 15 days ahead. And the configuration was, so here from the extended range forecast, we had 101 forecasts. And how they are produced. So this set of partial differential equations driving the atmospheric motions needs some initial conditions. These initial conditions are obtained from atmospheric observations, and there is one set of initial conditions which coming from these atmospheric observations, and the output of the system is the so-called control forecast corresponding to the two initial conditions. And after that, they start to perturb the initial conditions and provide 100 more outputs corresponding to these perturbed initial conditions. And that's what represents the forecast uncertainty. And these perturbed members are good in the sense that they can be considered statistically as indistinguishable. So that's why it's easy to handle them. So we consider only these 100 perturbed members, and we consider different ensemble sizes. So the horizontal resolution of this forecast were 36 kilometers, so 36 by 36 grids on the whole globe. We had 3 months of data, and we were verified it against observations. And we take only a grid, which is 1.5 degree latitude longitude grid in the northern mid-latitude, so between 35 degrees north to 65 degrees north. So these were our real data. And we needed multivariate forecast. How did we get multivariate forecast? So we had these grid points, and we first investigated as multivariate forecast horizontal dependence. We considered temperature at 850 hectopascal altitude, and as a multivariate forecast, we considered forecast for such a so-called 3x3 stencil. So we took 9 points, like you see in the figure, 1,000 kilometers apart from each other, and then we get a 9-dimensional forecast. So then we shifted by one grid point. The grid points are 1.5 degrees apart, so we shifted 1.5 degrees apart, get a new 9-dimensional, calculated the score. Then shifted once again, and what you see here in the figures, the mean scores for all stencils and for all 90 days, September, October, November, which we had. And what you can observe that the logarithmic score strongly depends on the ensemble size. So here is the green one is the 16-member ensemble, 24 members, and okay, 64 and 100-member ensembles are not so far away from each other, but still they differ. In the right panel, you see the same for the fair logarithmic score, and you can see that they are nicely close to each other. So they are pushed together. It doesn't really matter what is the ensemble size. We get the same results, so we can get a fair comparison. The next idea was vertical dependence. As vertical dependence as a weather quantity, we considered the so-called geopotential. Geopotential is the altitude where you have 200, 300, 500, and so hectopascals of pressure at a certain point. And we consider 6 pressure levels. So same location, but vertically you had 6 different levels. So we had 60-dimensional forecast, and the results are the same. again. So please switch off your mic. Okay, so you see again that the log scores different, whereas the FAIR versions have a very small deviation. And we also have something even more complex, because wind vectors are by nature bivariate, because we have a wind speed south-north direction and the wind speed east-west direction. And these two create a wind vector, which is, by the way, bivariate Gaussian. And we consider wind vectors at 6 horizontal levels. So at the end, we get 12-dimensional forecast. Naturally, now we cannot deal with 16-dimensional ensemble. So the starting is 24 dimensions, but the results are the same. And the fair log scores are not as perfect as before, so not as close to each other as before, but still the deviations are pretty small. I will explain the deviations a bit later. So that were our experiments. And now in this table, I summarized our results for different configurations. So this is the delta log S, is the difference between the 16 members and the 100 member forecast. And delta F log S, the same for the fair logarithmic score. At day 2 and day 5, so this is day 2, and here I have day 5. So in the previous one, I had, this is the 16-member ensemble and 100 ensemble. So this was the difference here, and this was the difference here. And, oh, sorry, I'm moving the wrong direction. So the light gray ones are the case studies I showed you that we also investigated 2x2 stances, just 4 points, 1,000 kilometers apart for temperature. We have 2x2 and 3x3 stances for wind speed. We have stances of geopotential at 500 hectopascal, 2x2 and 3x3. 3 pressure levels of geopotential. We have already seen 6 pressure levels of the geopotential. We had 2-dimensional wind vectors at 200, 500, and 850 hectopascals. We have wind vectors at 4 levels, at 2 levels, and we have wind vectors at 6 levels. So from 2-dimension, we range to 12-dimension, but the results are the same. So if you consider the ratio of the differences, just the difference in fair log score is 2 magnitudes lower than the difference in the classical logarithmic score, which shows us that it's really useful. Well, now one more question arises here, because here we assume that everything is Gaussian. But we dealt with real data, so naturally we wanted to test whether the data is Gaussian. And to test multivariate normality, we used the so-called Hansen-Zirkler test statistic, which we saw as suggested to be the most useful. It's built-in, it's the default test, for instance, in the R language for multivariate test statistics. And this is the form. It compares the kernel density estimator based on the sample with a true Gaussian distribution. And if you take the logarithm of this test statistics, it's Gaussian. And if you standardize it, It's called the Wald test statistics. It's a standard Gaussian. So just we can use a simple standard Gaussian test to test multivariate normality. And what you can see here in our figure is the Wald test statistics for different configuration. The last three configurations are the ones which I showed you. And what you see that these Wald test statistics, for instance, in this 9-dimensional configuration has a peak somewhere here at day 7. And since we compare it to the standard Gaussian, we can accept it Gaussian if the value is less than 1.96, so somewhere here. So at day 2, kind of all three can be considered as Gaussian. Whereas later, especially in this 12-dimensional configuration, you have a significant deviation from the Gaussian. By the way, here we simulated Wald test statistics for consider the Wald test statistics for simulated data, which are truly Gaussian, and you see they are all around 0. So here we have a large deviation, especially for this 12-dimensional. And let me go back to the corresponding figure. You see that the deviation getting larger and larger as we go on by time, but still it has some kind of robustness, and they do not necessarily should be Gaussian. And I have one more nice example. It's not my idea due to my partner Martin Leutbecher, namely the following. We consider a very simple 2-dimensional example where we have a 2-dimensional Gaussian observation and we have a 2-dimensional Gaussian ensemble forecast, and the means are correct. The true correlation for the observation is 0.9, and which means the marginals are a marginal distribution match. The only deviation can be in the correlation. So, and what we did, we generated samples of size 1 million for different ensemble sizes and estimated the mean fair logarithmic score for different correlations in the forecast. And look at the figure. So, in principle, minimizing the log score, meaning maximum likelihood estimator, so these curves should have a minimum at 0.9, which is the true correlation. If we consider the simple classical log score, 6-member forecast, minimum is somewhere here, 12-member getting closer to 0.9, 100-member forecast, you have sharply at 0.9, provides you a reasonable estimator of the true correlation. However, if we use a fair logarithmic score, 6 members are enough, and you get as a minimum the 0.9. Okay, it's a large sample approximation, so we can consider it as an expected logarithmic score. But anyway, for a 6-member ensemble, we get back as an estimate, as a maximum likelihood estimator, kind of the true correlation. So that was about the log score. And the other topic I'm going to talk about is the fair version of the so-called box ordinate transform, namely, again, for multivariate Gaussian forecast. So you have a p-dimensional observation and you have a predictive distribution. And this is the so-called box ordinate transform. Well, we know that this squared Mahalanobis distance has a chi-square distribution of p degrees of freedom, theoretically. So this is the uniform, and 1 minus this value is again uniform. So this is just tradition. We refer to this paper that we use this very version. So if the forecast, the predictive distribution matches the distribution of the observation, then we have here a standard uniform distribution, which is pretty nice because we just plot the histograms for all predictive distributions and observations, and if they are uniform, then we are fine. It's well calibrated. Obviously, we have an ensemble forecast, so you have an estimation. You use the estimator and you plug into the previous formula the estimators, which I will call as naive sample BOT. And this is one possible approach, but later Danny Wilkes suggested an adjusted version. The idea was the following. He added also the observation to the forecast. So you use not n, but n+1 values, vectors, to estimate the mean and the covariance matrix. However, it doesn't really matter because in both cases, these versions are asymptotically uniform when the ensemble size is again much larger than the dimension. So in this paper, he considered kind of 2-3 dimensional cases, and 100 ensemble size was around 100. And what we wanted to derive is the fair version of this box ordinate transform. So again, we started with these estimates and used the same trick as before. So we considered the squared Mahalanobis distance of the observation from the ensemble mean, and if the observation follows the same distribution as the predictive distribution, then this guy is Gaussian, this is an inverse Wishart, and we are at the same point as kind of half an hour ago that a transform of this squared Mahalanobis distance has an F distribution, which means instead of the chi-square distribution here, we consider an F distribution, and we have this correction term coming from this part. And this is what I will call a fair sample BOT. And whatever the sample size, whatever the ensemble size, under this condition this should be standard uniform. So we wanted to test whether it's really true, and first we want to use some kind of computer simulations. And the idea was the following. We followed the suggestion of Wilkes. We used the same type of simulation. And in the first case, we assume that we have an observation, p-dimensional Gaussian observation, with zero mean and a given covariance matrix. And we have this very covariance structure. This is a well-known covariance structure because what we had as a covariance matrix is an autocovariance matrix of a stationary first-order autoregressive process. However, again, there was some heuristic behind, because such a first-order autoregressive process can serve, see the reference here, as a model for daily minimum or maximum temperature. So you could see these p-dimensional observations as a sequence, as a vector of daily minimum temperature for p papa subsequent days. So this was the observation. And we had a forecast. which can be biased, has a mean, and has a covariance structure of the same shape, only the variance might be different, and this autocovariance can also be different. So this was the simulation setup. And our forecast is well calibrated if these parameters just match. So, and we considered different types of misspecification of the predicted distribution. The first idea was that, okay, no bias. So mu is 0, but we either has misspecified marginal variance, so autocovariances are the same, variances differ, or fixed marginal variance and misspecified correlations. By the way, later we consider also the mixtures, but I won't show it here. This was one idea. The second idea was a bias. And the bias, we consider this in a special way because since this is a Gaussian distribution, kind of you have as a confidence bound a prediction ellipsoid at a given level. And we consider kind of the principal axis of the prediction ellipsoid, the first principal axis, the second principal axis of the prediction ellipsoid, and we considered bias in the positive direction, negative direction, positive direction, negative direction. So that were the different options for the bias. So that were the transformation, and we wanted to check how well do these BOT transforms work. And here is our first setup, three-dimensional forecast, three-dimensional 50-member forecast. And what you can see here is the true parameter values are variance 1, autocorrelation is 0.6. We perform 10,000 simulations, and the first row corresponds to the calibrated forecast when the forecast distribution matches the distribution of the observation, which means this we should get uniform distributions. And the second column is the theoretical BOT. So this is the ground truth. The D is the Kolmogorov-Smirnov test statistics, and the p-value is the p-value of the Kolmogorov-Smirnov test for uniformity. Here you can see that our fair sample BOT provides the same uniform distribution, a bit smaller, even a bit more, but still a larger p-value. The naive sample BOT rejects uniformity, whereas the adjusted also produces a bit of harm shape that, okay, it's uniform-like. When we under-forecast the variance, so autocorrelation the same, variance is a bit smaller. This is the ground truth. It biased towards the lower bins. All figures are of the same shape and roughly have the same Kolmogorov-Smirnov test statistic values. Over forecast, bias to the opposite direction. Shapes are the same. Well, naive is a bit lower Kolmogorov-Smirnov test statistics, but roughly we see the same picture. So all forecasts behave similarly. Now, variance is fixed, correlation under forecast, correlation over forecast. Naive is a bit of outlier, but the one suggested by Wilks is close to the theoretical, and our also performs well. So P3, sample size 50. P3, sample size is just 10. Calibrated forecast, theoretical BOT accept uniformity. Our fair also accept. Look at the naive and the adjusted sample BOT, biased completely. So none of them can be used for checking calibration. And again, if you consider different types of miscalibration, then you see that our fair shows the same histogram as the theoretical one. Naive is highly biased towards the lower bins, while the adjusted sample loses weight in the very lower bins in all cases. So you see the same phenomena that in the left two figures you see something similar, but the other two guys are completely different. So, and the same applies for correlation under forecast or correlation over forecast. We also checked what happens if we large sample size, large ensembles, dimension and large ensemble size. So the ratio of the sample size over ensemble is even worse. But you see, again, okay, I admit we are not as perfect as before, but here for the calibrated forecast, we still see the uniformity. But these histograms completely kind of out of the track, gives you completely false shape, whereas the fair version works rather well. Okay, now we wanted somehow to estimate what will be the reasonable sample size for a given dimension. So what we did was the following. First, we also investigated the bias. So as I mentioned, we consider the bias in the first principal axis, positive direction, negative direction, second principal axis, positive direction, negative direction, large ratio, 50/3, all figures look the same. The first, the second, and the last one gives roughly the same Kolmogorov-Smirnov test statistics. The naive is a bit out of track. Here, when small sample size, 3 dimensions, again, the first two result the same figures and close values of Kolmogorov-Smirnov test statistics. Here you can see completely different pictures. Again, this confirms the superiority of the derived fair version of the sample BOT. Now, what you can see here, all of these figures are based on 10,000 simulations, 10,000 forecasts of different sizes. Now we repeated these 10,000 simulations 1,000 times, and we calculated the proportions of Kolmogorov-Smirnov test which reject uniformity at a 5% level. Properly calibrated forecast. So in general, they should be formed in this case. And what you see, the solid lines correspond to the fair sample BOT, different colors to different dimensions. However, whatever the dimension is, all these values are pretty close. Whatever the dimension, whatever the ensemble size, close to the desired 5%. The dashed line correspond to the best performing classical adjusted sample BOT. And you see that even in 2 dimensions, we need around 100 samples to get close to the 5%. For 3 dimensions, you need around 300, and so on. In certain dimensions, around 1,000 samples getting closer. So again, we see the superiority of the fair version. And We also consider the detection power of the Kolmogorov-Smirnov test in the case where we had a fixed correlation and deviation in the variance, or a fixed variance and the deviation in the correlation. So the true value was here 1, and the solid lines behave as supposed to be. At 1, they have the minimum. You have a classical U shape, whatever the combination is, and the minimum is at 5%. Whereas for the adjusted sample, even in the best case, when you have 53-dimensional ensemble forecast, you have some kind of U shape, but the minimum is around 0.45. All other two cases result in just flat values, so no detection power at all. And the same you can see where you have the forecast correlation. The true was 0.6, which is nicely achieved by the fair versions. And finally, we tried the same with operational forecast. First of all, we consider a perfectly reliable situation, which means we consider the 100-member forecast. We picked one of them to play the role of the observation, and the remaining ones were the forecast. And we calculate, so this should result a uniform distribution. And in this case, for the 9-dimensional stencil, temperature at hectopascals, at day 2, it's Gaussian. The fair sample BOT, whatever the sample size is, results in something which is uniform. Adjusted for a small sample size is hump shape. And of course, if we increase the sample size, getting closer and closer to the uniform distribution. Whereas the naive, still getting better and better, but still biased. At day 10, which is not Gaussian, even the fair, close to the uniform, but it shows some U-shape, some deviations. In the other two cases, we see the same. So they cannot be used to check the calibration of the forecast. Also, these were perfectly calibrated. So this was the horizontal dependence. And this is the 12-dimensional case, which vectors are clearly non-Gaussian. The longer the lead time, the least Gaussian they are. At day 2, we have U-shape, but much better. At day 10, okay, getting closer to the uniform, but not perfect. But again, compared to the other two guys, it's still much better. So these are also robust a bit, but not as nicely as previously. And finally, we considered the forecast against the observations. The first corresponds to the 2-dimensional wind vectors. And this shows you that wind vectors are nicely Gaussian, we tested it, and well calibrated. So all histograms are uniform. So for temperature and horizontal dependence, 2x2 and 3x3 stencils, they are not Gaussian. And what you can see, a bias towards the lower bins. And for the 12-dimensional case, wind vectors have 6 pressure levels. We see the same. So what we see here is some kind of bias, but these figures are similar to the simulation figures where we have the biased data. And we check the data, and the forecasts were biased, but they nicely captures the correlation structure of the observation. So indeed, these forms indicate us biased forecast, but no miscalibration in the covariance structure. So to summarize, what we found that for the log score, the ensemble size adjustment works quite well, and whatever we consider, the results are very consistent for all lead times and dimensions. And also we assumed everything to be Gaussian. The dependence is well approximated even in the situations where the deviation from the normality is substantial. So it can be well used for testing ensemble configurations or comparing ensemble configurations with different ensemble sizes. Again, the fair version of the BOT corrects nicely the deficiencies of the sample BOT versions in the case when we have high dimensional predictors or small ensemble sizes, so their behavior is roughly independent of the sample size dimension ratio. So it provides a powerful tool for testing calibration, and it still exhibits some robustness against deviations from multivariate normality. Of course, if are highly non-Gaussian, the data, then it departures from the flat sample BOT histograms. And with this, I would like to thank your attention and looking forward to the questions.
Okay, thank you for your nice talk. And any questions? And I have a question for non-Gaussian case. What distribution do you have? Do you have heavy-tailed distribution, or it is a mixture of several Gaussian distributions?
Well, usually it depends. So what we exactly know are the marginal distributions. For instance, if we have a wind speed, then it's not necessarily a heavy tail, but a skewed distribution. So non-negative, and the skewed, for instance, either a truncated normal. So you do a truncated normal distribution at 0. But when we consider this kind of wind speed at different levels, then separately they are truncated normal, but possibly with different parametrization. So to be honest, together as a multivariate distribution is far from being clear what kind of distribution do we have. So, but different, okay. Yeah?
You could try to use a mixture of two Gaussian distribution and instead of a single Gaussian distribution.
Yeah, we have such an approach. The problem is that in this case, even a bit more difficult. So for a mixture of Gaussian, maybe we can derive the box ordinate transform, or we can derive a formula for the log transform. But to be honest, we haven't tried.
Mm-hmm. And any other questions? And I have more general questions. So you constructed an unbiased score function, yes?
Yeah.
And I understand as a result, if your sample size tends to infinity, then your forecast will converge to the best possible forecast. Am I right?
Yeah, indeed.
That is the reason for you are looking for unbiased score.
Yeah, exactly. Exactly. So in one of the first slides, I also told that then the score is minimized when the forecast distribution meets the distribution of the observation.
And if you increase both your dimension p and the sample size, then maybe in a limit we have some interesting distributions if we increase them in certain proportion.
Yeah, probably. Well, if yes, I assume that if the proportion goes to some limit, fixed limit, then I think we can be fine also and have the same result. But wait a second, because practically in the fair version, we somewhere have the ratio of the sample size. So in formula, which we derived for the fair version, we have the dimension and divided by the sample size. So yeah, if we can regulate somehow the limit of this convergence, of this ratio, then I think we can get again some limiting version for this fair score. But I don't know what kind of, so what will be the outcome for this. But as practical experiments showed, even with a very small ratio, we were able to get quite reasonable results. So three-dimensional forecast of size 10 provided reasonable values.
Okay, thank you once again. And any other questions? Arnold, did you want to ask something? No. And so you use this methodology for real weather forecasts or not?
Yeah. Recently, I'm a fellow of this European Center for Medium Range Forecast, so kind of I have a direct access to their forecast data, and I have quite an intensive work with the colleagues here. I often appear in the United Kingdom, and we use them so we test it for real forecast, because these ensemble sizes usually determine their configurations. So what kind of forecast configuration should they produce in the future? So for instance, earlier they had 51 forecast, but on an 18-kilometer grid. Now they reduced it to the 9-kilometer grid, but introduced another 100 forecast on a coarser grid. So, and to evaluate this forecast, they can use this type of results.
And when I was visiting Texas in USA, then I noticed that their weather forecasts are very, very precise. For tomorrow, they give perfect forecast. And even for 2 days, almost perfect. What methodology do they use in the USA?
In the USA, so in this ensemble forecasting, in this numerical weather production, so the NOAA in the USA and the ECMWF in Europe were the pioneers. They introduced their ensemble forecasting systems in 1995 and 1996, and practically they used the same type of techniques. So, but ECMWF uses a larger ensemble size. In the USA, they have, I think, 25 members or something like this. Here they have 51 members. But roughly the same type. Of course, there are differences in the equation systems, but the same type of ensemble prediction systems they operate.
So normal distribution is marching all over the world.
Yeah, so kind of there are no doubts. So for temperature, so a normal distribution we assume here, but usually they start with the rows. So in the modeling, they do not use normal distribution. Then later, right now, when they want to evaluate the forecast, or what I'm doing mainly post-processing, which means fitting a probability distribution, then we quite often use Gaussian distribution, easy to handle and suitable for a lot of cases. There are some situations where the data are not directly Gaussian, but we can use, say, a Box-Cox transformation to make them closer to the Gaussian. And we also have some kind of robustness in the techniques. So even if they slightly deviate from the ocean, the asymptotic results are roughly the same.
Okay. Maybe Professor Maybrada wants to ask something.
No, I have no questions. It was very interesting. It was interesting algebra. Unfortunately, I did not understand how the forecasts were made, but it must be another long story. Maybe Professor Baran tell us sometime how it is done. It was about how to choose the best forecast from the given one, but how the forecasts are built, it was still open question. Thank you very much. It was very interesting.
Honestly, to answer a question, to explain you how exactly these 51 forecasts are made, I'm not the right person. So, because once I try to understand this system of equations, they are available at the ECMWF website, exactly what is the physics behind it, what are these dynamic equations, and how they generate the how do they generate the perturbations for this set of partial differential equations, but I won't dare to try explaining you. So what we start, but our input data are the forecasts themselves. And then we do something
anyway,
with
you solved some equations to build your forecast.
Yeah. A very complex set of partial differential equations. Well, now what is the future is machine learning. So they are testing, they are the first in the world to operate machine learning based forecast trained on 40 years of data, and it's getting better and better. So fully data-driven forecast, and the performance is comparable with the traditional physics-based forecasts.
Okay.
Thank you. Thank you.
And next time probably we have a very applied talk on radar systems and some statistics hidden in radar system. My former PhD student Andrei Malenko intends to give a talk. Okay.
Okay, thank you very much. I will
Thank
pop
you.
in next week. I will have classes at this time. Before the talk, I have just finished my class on statistics here at the university.
Okay,
So
we are very glad to have you as a speaker.
thank you very much for inviting me. And well, I think things will better. So what I would say, Slava Ukraini.
Героям слава.
You heard probably that we have nice changes here in Hungary as well.
Yes, we follow the changes
Yeah,
closely.
we are very happy about it. At least I am very happy about it.
Yes.
And maybe it also helps for Ukraine a bit as well.
Yes, it is very important for Ukraine
Yeah,
what happened in Hungary.
yeah, I know.
Okay. Give my best regards to Istvan.
Okay, I will forward. Okay.
Okay. That's all.
Okay, thank you very much, and bye for everybody. Thank you having me on your talk. So,
Bye.
bye-bye.
Goodbye. Bye.
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 Bye.